So you want me to share the screen here, right? Great. Okay, now I need some room for this. Just a second. Yeah, well. Yes, this is going to be some low tech. No worries.
Okay, so we had the crystals. Now we move to Lima triangulations. It's my pleasure to have Petar Pavesic telling us about it.
Yes, thank you very much. Thank you for the opportunity to speak here. We are restarting our live sessions, scientific, and so I'm very excited to do this. Okay, today I'm going to give you some low-tech presentation of one problem and one tentative answer to that problem, which is both theoretical but also has some, practical aspects. And I'm going to give you this, these two things, kind of try to tie those two things together. So first of all, this is joint work with Dejan Govc and Wacław Marzantowicz. And it starts from a really simple-minded question. If you want, you have a triangulable space, compact one, and then you just ask how many simplices are actually needed to triangulate X. Well, you know that in general, we often in geometric topology and algebraic topology, we work with spaces that have triangulations, but I mean, we usually don't need explicit triangulation. It's different if you do applied topology, because then often, I mean, the only fact the space can be triangulated is not of, is often not of much help. You need a specific triangulation, and then you want to know what is it. So, I mean, why should we care about this question? Of course, first of all, it's a well-posed question, so I mean, mathematicians should try to give an answer. But also, from the practical viewpoint, so assume that you have some cloud of points, and you, I mean, suspect that it is some space. So the first kind of question is, well, can this cloud represent this space? And the thing that you can check, well, I mean, do you have enough points to represent the space? Or from the other viewpoint, I mean, how many points do you need to model some space? Okay, so I mean, sometimes you want to perform some computation, some combinatorial computation. I'm going to give you a specific example a little bit later. And so, I mean, you want a specific model of the space. Or on a more general level, I mean, we have all kinds of data, all kinds of data, and we are looking for new invariants, right? I mean, today we all already heard about using Euler calculus or persistent homology or other things. But I mean, of course, there is a huge toolbox of different things in algebraic topology that one can use. So, for example, what if we compute the corresponding ring structure in cohomology, cup products? Or maybe we have even some characteristic classes, things that can be computed and can be used to distinguish between cases. Well, I mean, here the situation is a bit disappointing, because most of the time additive structure is enough. Most of the time your data turns out to have the homotopy type of a wedge of spheres. So in a sense, it seems that the wedge of spheres is a dominant case, is a generic case, if you want. Well, that's maybe true, or maybe it's not, depending on the viewpoint. So, I mean, I think that after this talk, there you may have a different opinion. Maybe it's just that we are using small samples. And when I say small, it's okay. We will start with dozens of points, then maybe hundreds of points, but it will increase fast. So, okay. So the question is, given a triangle space that admits a triangulation, and all axes here will admit triangulations, and manifolds will admit PL triangulations, combinatorial ones. I'm not going into but I mean exotic things. So there are two questions here actually. So one of them is estimate the number of all simplices. Well, I mean, number of all simplices increases exponentially with dimension. This is obvious. This happens for the sphere, so we don't expect anything less. I mean, we expect just exponential growth and a big exponential growth. Okay, so and also there are other techniques that are used to estimate this. There are different versions of so-called lower bound theorems. Starting from 70s with Barnett, then Kalai, Macmillan, Adiprasito. So there are some recent developments in this area. And I mean, here you are able to look at Betti numbers of your manifold and estimate what's the minimal number of simplices that you need to construct it. And then this number is usually highly exponential. Well, but I mean, you are not usually representing your data by listing all simplices. You are usually just giving the points and then facets, right? So, I mean, you are actually interested in the zero-dimensional simplices and then the top-dimensional simplices. This kind of measures your data. And also for all of those theorems, usually the number of points is an input. So, I mean, you start with the number of points that you have, and then you estimate the number of simplices or facets that you need to triangulate your space. So, I mean, in this talk, I'm going to discuss only this, I mean, base case. So, what is the number of vertices that you need to triangulate some space? Okay, so I mean about this. Okay, I need to point just a second. About this kind of exponential growth, I'm just giving you some idea. So think of it, if you want to triangulate a sphere, like an n-dimensional sphere, then you need n plus 2 points, okay? I'm going to mention results, what happens if you need to triangulate surfaces, maybe some more complicated spaces. But I mean, the immediately next level, like a Grassmannian, and not a very big one. So I mean, this is 3-dimensional subspaces of R8. It turns out that at least 250 million simplices are needed to triangulate. So I mean, and this is probably very much underestimated. I would expect orders of magnitude bigger real numbers. I mean, these are only lower bounds. So I mean, this means that it's really hard to find non-trivial cohomology product, non-trivial characteristic classes. I mean, if you expect how many points do you need to find a non-trivial characteristic class in a space, then like a Stiefel-Whitney class, you need a lot of points. But we know that there are spaces which have non-trivial characteristic classes. So I mean, how on earth are we going to find them? Okay, so let me just introduce this notion. So this delta of x is just defined to be the minimal number of vertices in a triangulation of the space X, minimal possible number, right? And for manifolds, we usually understand minimal possible number for combinatorial triangulation, so PL triangulation. Okay. Very little is known actually about this. So I'm going to mention just, probably I'm going to list most of what is known. So first, we have spheres, and here the answer is simple. You need n+2 points to triangulate an n-dimensional sphere. Then there is this famous result about surfaces. So closed surfaces can be triangulated by this number. So this is 7 plus, well, some square root of this. But I mean, you can read it as approximately 3.5 times the square root of the genus. Okay, so this is approximately the number. There are also three exceptions, but don't care about those. So this is a combination of two papers, one by Ringel in 1955 and then by Jungermann and Ringel in 1980, which computed those. It's similar, it may remind you of this chromatic number of certain graphs. But the point here is that you see here the number of points increases linearly with the dimension. Here, dimension is fixed. It increases as a square root of a genus. Okay, so this is really slowly. I mean, you can triangulate a big, I mean, connected sum of many tori with a really small number of points. And then these triangulations are incredibly tight. Most of the time, the one skeleton is a full graph or close to being a full graph. Then there is only one more infinite family of cases. This is so-called Chasar tori. So these are just some d-dimensional bundles over S. So d-dimensional sphere bundles over S1, and they were computing. So this number is essentially again linear in the dimension. And that's all as for infinite families. Then there is about a dozen examples of specific spaces for which the minimal number of simplices of vertices was computed. You can find them. There is a really nice paper preprint by Frank Lutz, and that's all. And examples are just some products of spheres, some projective spaces, and a few more cases. And even for this last one that is listed here, so the Quaternionic projective space, this is just a really recent result which required a computer check, because there was a, okay, let me show this. There was a famous triangulation proposed by Brehm and Kinner in 80s, which they thought that was a triangulation of the Quaternionic projective space. It had 15 points, and then you say, well, I mean, you can check that it is a manifold. It has the right homology. So, I mean, a computer should be able to check whether this is a Quaternionic projective space or not. Well, it's not that easy. I mean, there are two possibilities with that cohomology. They are distinguished by first Pontryagin class. Pontryagin class is, well, in general, that's a diffeomorphism invariant. It's you cannot compute it directly from a triangulation unless it is the rational first Pontryagin class. It can be computed. Method is very complicated. There are formulas introduced by Guy Thulin in the between 2005 2010. Anyway, Gorodko was able to compute this in 2016, and he had to check by computer and manually around 3,000 links of vertices to see whether, I mean, and there is an algorithm for each of them that computes the Pontryagin class, and then he showed that this is actually the Quaternionic projective space. So the problem was set from like 5 years ago. And this is only 15 vertices. Okay, so let me say what can be. So, I mean, today I'm going to concentrate on lower bounds. So on saying what's the minimal number of vertices that you need to to triangulate certain space. Okay, not only using additive structure, but also some multiplicative structure. And here, the first attempt will be very simple-minded using Ljubljana category. So Ljubljana category, you can think it of a way to decompose space into contractible subspaces. Well, not contractible; those that are categoric, so can be contracted within a space. But this is close enough for our needs. So the idea is the following: if you know that the category of a space is, say, n, then by standard results you know that this space has dimension at most n-1, which means that somewhere in your triangulation there are endpoints which span a simplex, because otherwise your space is not of dimension n. And so you can remove those. You can remove those endpoints and also its simplicial neighborhood. And what remains is a space that has a category at most, at least, sorry, n-1. Okay. And then you repeat this. So, I mean, then there must be at least some points so n-1 points that span a simplex. Again, you remove the simplex and its simplicial neighborhood and continue this story until you have one point left. And then you remove this last point and you count everything. And so this is extremely simple-minded, and you get this this formula which says, okay, the number of vertices is at least category times category plus 1/2. So essentially category squared. Half of category squared. Well, I mean, this is simple-minded, but for small dimensional examples, it gives the precise or almost precise value. Okay, and one more thing, it turns out that this is the best that at least we are able to say in the case that the category is equal to dimension plus 1. So all improvements that I'm going to talk later are for the cases where category is not detected by dimension, but is detected by other invariants. Okay, so I mean, this argument is going to show up again and again. So are there any questions at this point? Okay, if not, let me continue. Oh, yeah. No, at least not to me. Okay, so I must say we computed a lot of examples and classes of examples, but we didn't try all of them. So I mean, I'm going to present some machinery, and then you study different cases, and you can try to compute something once you know a little bit more about those spaces. I mean, category. So Cipher manifolds are of category 4 most of the time. So this gives you, but this gives you a general estimate. So this is like they need at least 10 points. I would hope for a better estimate than just this, right? So for spaces of small category, but as I said, this is a basic idea, and then the basic it gives you some small numbers. But again, as I said, so this is a precise number for complex projective plane and it's close to it for some projective planes. But then it seems that there is a divergence between these estimates and the real values. Values start to grow really fast. Okay. So a better, a refined approach would be to use cohomology ring. And again, the idea is quite similar. So I mean, what you do is you take a non-trivial product in cohomology, and then you say two things. Well, first, this non-trivial product detects some dimensions. Okay, so I mean, if you have a non-trivial product, then it means you look at the dimension of this this cohomology class, and then you know that there must be a simplex of that dimension. Because, and I mean, sometimes you say, well, there must be many simplices of the dimensions. This is not necessarily true with minimal triangulations. Minimal triangulations are extremely economical. So I mean, you can have only a few top dimensional simplices which determine this. Anyway, but there is at least one, so you can remove that one, and you can remove its neighborhood. And then again, when you remove this neighborhood, the usual trick shows you that, of course, the entire product does not survive, but all of its subproducts survive. I mean, strict subproducts survive. So you can iterate. And then again, you can count this thing. And counting gives you this estimate. So, I mean, you take the product, then you take dimension of the first one, and then the second one was counted twice. So it is 2 times the dimension of the second one and 3 times the dimension of the third one. And it clearly makes sense to order them by dimension. So you get a bigger estimate. And so you get this, this sum. Now, clearly, if all elements in the product are of dimension 1, you get the same estimate as before. But this really improves things if you have products with elements of dimension that are bigger than 1. And so again, let me just give you some numbers just to give you some idea. So for projective spaces, this gives you approximately half of n squared. For complex projective spaces, it gives you approximately n squared, and so a dimension squared. I'm sorry, not dimension, but the CPN. So n squared, and for Quaternionic projective spaces, it gives you this, so about 2n squared. For the lowest dimensional cases, so for n is 2, these values are precise. For a bit bigger, they are close to them, and then, as I said, they diverge. And as far as I know, I mean, I don't know if there is a known triangulation of CP4. So there is a famous triangulation of CP2 with 9 points or 9 vertices. I think that I've seen one for CP3. I'm not aware of the triangulation of CP4. I mean, readily available triangulation. So I would be happy if any one of you knows a specific triangulation of that space. Anyway, I mean, if we go to slightly more complicated spaces like Grassmannians, then again, we have a paper just giving some estimates. So I'm just giving you some sample. If you look at the Grassmannians of planes, then the number in Rn, then the number of simplices of vertices is at least 2n squared. For 3-dimensional subspaces, it is about 4.25 n squared, and then it is 7n squared, and then it increases, and we don't have a closed form formula. So I mean, I would say that this says that we need really many vertices to triangulate those. And as far as I know, I mean, again, I don't know any specific triangulations of those spaces. And I mean, I want to remind you, it's really easy to make a cell decomposition. There is a CW decomposition with a small number of cells for each of those. It has, I think, n over k cells, but those cells are attached in a homotopic, in a really non-trivial way. So I mean, and this is now shown in the number of vertices and simplices in general that you need. So I mean, okay, this is just an example, but I think that we computed if you try to triangulate, I think 8-dimensional subspaces of R20, the number of simplices that you need is bigger than the number of particles in the universe. Okay, so can you say that something like this has a triangulation in any meaningful way? Well, only in our heads, I think. Okay. Let me continue now with this idea. So first of all, we are clearly talking only about compact manifolds, right? And compact spaces if we want finite triangulations. But actually, if you want to change your spaces up to homotopy, you can try also non-compact spaces, at least those which are homotopy equivalent to finite complexes. So this is another concept which is going now in the rest of the talk is going to replace this delta of X. It's called covering type of X. This was introduced by Max Karoubi and Charles Weibull in just a couple of years ago. And it's, again, it is a simple invariant. You just say, well, Ct of X is just the minimal size, minimal number of elements in any good cover of X. And you all know what is a good cover. Good cover is just a cover in which all subsets and all intersections, finite intersections, are contractible. Normally, you take an open cover. There is a way, I mean, in some cases, you can take a closed cover and so on. But anyway, so covering type, maybe not really a good name for the concept, but anyway, covering type of X is just the minimal size of such a good cover. And okay, so I mean, since we know that X is always homotopy equivalent to the nerve of this cover, we can just say that, well, then the Ct of X, or the covering type of X, is just the minimal size of a homotopy triangulation of X. So, I mean, the minimal number of vertices that you need to build a space that is homotopy equivalent to X. And again, this is closer to our way of thinking because all of our invariance category and cohomology are actually homotopy invariants. So we are measuring homotopy invariance. And yes, so number of simplices that you need to triangulate X is clearly bigger or equal to the covering type of X. It's interesting that for manifold, it's actually can be smaller, but as far as we know, not much smaller. So in a sense, we have a homotopy estimate for something that is probably, I mean, only a topological invariant. But okay, that's still open. So, and yes, it is not surprising that the previous invariants actually estimate a lower bounds for the covering type of X. So from this point on, I'm going to talk only about the covering type as a proxy for the number of vertices. Okay. Well, important thing here, I mean, a useful thing is that it's homotopy invariant and that it applies to non-compact manifolds, non-compact spaces, at least if they are homotopy equivalent to compact ones. And there is one important example that people work, especially in topological robotics, which is kind of my field of interest. And these are configuration spaces. Configuration spaces, say, of a certain number of points in Euclidean space. These are highly dimensional spaces, but they homotopy deform to spaces of lower dimension. And if you want to do computations in topological robotics, you are interested in the homotopy type. So essentially, you want to build models finite models of these spaces. And again, the cohomology of those spaces are known. And if you want to triangulate them, again, you get quite a big number of vertices and then the huge number of simplices facets that are needed to compute, to triangulate those. So again, this seems to be practical only for relatively small d and n, after which it becomes, computationally unpractical. Okay. So now, in a sense, the last theoretical section is this one. So as you've seen, we have this basic simple-minded category estimate. Then we have somewhat refined estimate with cohomology, which is really a big improvement if you have products which have elements of higher dimension. So the next step that sometimes work is if your cohomology classes have some weight. I mean, a cohomology class has weight at least 1, but it can have a higher weight. So this is maybe not such a well-known concept. So let me recall what is it. So a cohomology class has category weights. So the category weight is just the minimal number that is, I mean, minimal k for which u restricted to a subspace of X is 0 whenever category of A is at most k. Okay, now this is difficult to read, but the way that I usually think about this is, I mean, category. So you can think your space is padded with some constructible subsets, and then you get a guy that walks around. And if this cohomology class is of weight 1, then it can stay on. I mean, it sinks if it stays only on one of those platforms, but it can, I mean, float if it stays on 2 or more platforms. Okay, and then you have heavier guys that sink 2 platforms, but can stay on 3 or more. So that's in a sense the way that you can think about the category weight of a cohomology class. Well, unfortunately, this concept is not homotopy invariant. So there is something that is called strict or essential category weight. So the first concept was introduced by Fadeli Hussein in '92, and then it was refined or homotopy invariantized, if you want, by Jeff Strem and by Yuli Rudiak in the late '90s. And they just said, okay, the category weight is just this number. So this is a minimum of category weight. Strict category weight is the minimum of category weights whenever you map, when you pull back this along a homotopy equivalent. So in a sense, essential category. Okay, now what are the main properties of category weight? Are the following. First of all, this is a number between, it's at least 1 for ordinary cohomology classes, and it's most the dimension of the element, and also it's at most the category of the space in which they live. Then the second thing is, and second and third are actually the most important for computation. If you pull back a cohomology class, its weight can only increase, it cannot decrease. And the second thing is, if you take a product of elements, then it is super additive, which means the weight of the product is at least the sum of weights, and it can be even bigger. And then for computation, I mean, and for finding classes of non-trivial weight, the weight of classes that come from the cohomology of discrete groups is exactly their dimension. So essentially, you classify your cohomology class, pull it back, look what is I mean, and then dimension does not increase, so that the weight of those elements are at least what you find in the cohomology of the. Okay, so now this is a computational machine that you can make work, and the main thing here, so the main idea is that if you can say that your space is built by adding, so taking some core space and adding 2 categorical sets up to it, and then assume that you have a non-trivial product of this kind. Well, by removing 1 categorical set, then as usual in category theory, you know that u times v is 0 at the remaining space, but both u and v are non-zero. Okay, so this is for normal category. Well, for weighted category, it means that if some of those has weight 2, you are allowed to remove 2 categorical sets, and still the complement, so the complementary product is non-zero. Okay, I mean, this can look as a small improvement, but most of the time this just doubles your estimates, because now you can repeat this story and you get much bigger sums. So that's again this is the central idea, and then there is the things become complicated because now you have two parameters to look. You are looking for optimal dimension of elements and for optimal weight of elements, and you want to balance those. And most of the time it happens that elements of higher weight are some middle dimensional ones, and then you have some high dimensional ones. You want to keep them in the sum as long as it makes sense. So it becomes quite quite complicated computationally, but you can do it. I'm going to skip this outline of the computation, and I'm just going to okay. Oh yes, and then there is another problem. So you would like to say, well, in our formula, let's put strict category weights everywhere. But the problem is, as I said, you don't know which is a category weight. You know that the category weight is at least something. It's at least 1 for all elements. It's at least 2 for some elements. And then by taking pullbacks and by taking products, the weight can increase. And I mean, you have absolutely no control over that. Unless it is just maximal with respect to the dimension, but most of the time it is not. So I mean, it's a relatively subtle element. So if you want to give some formulas, then we introduce something which is called weight estimator. Now this is getting really technical. So weight estimator is I would describe it. This is the best of our knowledge about what's the weight of the element. So you can always put 1, but then you didn't gain anything. For elements that you know, you put 2 or 3. I mean, depending on the category weight that you find, and live with it. I mean, and maybe it's bigger, but who knows? Anyway, if you do these things, then I'm just instead of going through details, I'm going just to show you the formula. Formula is a bit more complicated. It says that the category, the covering type of X is bigger than this block, right? So this is 1 plus the weight of certain product that you find, and then a maximum of some numbers, right? And then you can maximize over all products. But this is not, I mean, what you usually do. You usually just find some good product, a non-trivial product, and compute on this. I mean, cohomology is such that you usually know what's the right guy to take. And of course, I mean, if you take the weight of an element is 1, then you get the previous estimates. So you're looking for cases when you have elements of higher weight. Okay, so so this is the final formula, and I'm now going just to list some results, and then maybe so I have some 5 to 10 minutes. Where is okay, I'm going to cut this short if possible. So okay, so here is a list of cases when this really improves the thing. So if you start with length spaces, there is not a real improvement. But when you start multiplying length spaces or length spaces with spheres, then weighted estimates just double or even triple your previous estimates, and already give some relatively big numbers. If you want to triangulate a product of length space with a sphere, you need a lot of vertices. Then manifolds with finite, especially finite cyclic fundamental group, always have some cohomology classes of high weight, and then you can do computations. Non-simply connected groups, similar case. Orbit spaces of highly connected manifolds, which means manifolds which have only top dimension and middle dimension, at least in their Morse decomposition. Then products of what's called symplectically spherical manifolds, they have then the symplectic class has category weights too, and again you can improve the results. And okay, so now there are formulas, and probably there is no sense going through them. Let me just at this point say what you should have as a takeaway from this talk. So first of all, there is this question about the size of triangulation that you have. It is relevant whenever you want to compute something explicitly with spaces. It turns out, so I mean, we developed estimates using cohomology and weighted classes in cohomology. Most of our estimates give that the minimal number of vertices is at least of the order of the square of the dimension, with some coefficient, which is usually like a couple of units. So not, experience shows that for bigger dimensional spaces, this is very underestimated. In a sense, we expect that the real numbers are much bigger. There is much room for improvement in these results. But already it says that if you want to model spaces or to find spaces that have some non-trivial cohomology products or some non-trivial characteristic classes like Grassmannians, you already need a huge number of vertices and then an extremely big number of simplices. So this kind of justifies this experience that most of the spaces that you find that you try have, I mean, everything except additive structure is trivial. You get just wedges or spheres because simply you need a lot of vertices and simplices to build mildly complicated spaces, at least from the viewpoint of algebraic topology. Okay, so I think this is the right place to stop. Thank you.
So questions? Any questions? Okay.
What is the answer for the length space?
Okay, let me return to length spaces. Okay, so you get just this number. So for a 2n plus 1 dimensional length space, independently of the prime, it is approximately 2n squared. Okay, but as soon so I mean the interesting thing is that as soon as you multiply this by an m-dimensional sphere, which should be relatively simple, right? I mean, because you can build a triangulation from one from the other. You get this, so you get another twice dimension of the sphere, which multiplies n. So this is essentially the same number as before with 2mn, so twice the dimensions, the product of the dimensions, yeah. Which is much bigger. This is approximately 3 times as big as if you make the standard cohomology estimate 2.8 times on average.
What is funny that really that you mentioned that for length spaces, the cell decomposition is quite simple. So that then you can make a refinement of the cell decomposition to get triangulation. Even you make it, you have this kind of estimate, right?
Yeah. I think that the case of Grassmannians is even more, I mean, illustrative if you want, because I mean, for a Grassmannian, you need n over k, right? Cells and very nice Schubert cells, very nice description, symmetric and everything. And then you take, I mean, in order to triangulate, you need like hundreds of millions of simplices more than what you needed with cells. So, I mean, that's amazing for me, right?
Yes, hi. What is the motivation of Wacław and Kobe for introducing this? Do you know?
Oh, yes. It's a completely different one. It's actually closer to your field. So they're comparing cohomology, values of cohomology theorems, right? You take different cohomology theories, and then if you know how different are they on the level of contractible sets, then the covering type gives you some estimate of how different are they on any space. So that was they were comparing, I think, some algebraic, some cohomology theory coming from algebraic geometry to K theory, and that was just a very rough estimate of how different they can be. You can find, so there is this paper by Weibel and Karoubi, and they give a reference to that. So yes, that's another thing. That's a really coarse, not very refined instrument, but yeah, that was their motivation.
So I actually have two questions. So you have been discussing length spaces and Seifert manifolds. In dimension 3, do you know anything about hyperbolic manifolds? Can you give estimates there?
Okay. As you probably noticed, our estimates in dimension 2 are lousy. Okay. Because somehow, you have estimates that go up in dimension, which is like with cohomology products, weighted and so on. And then you have triangulations that go, if you want, horizontally. So, compute the genus and depends on the genus. And the similar situation is with hyperbolic spaces. So, category estimates and everything. This just gives you, okay, you need at least 10 or so for the projective, not for the length space, you need at least 10 vertices. Well, I think the minimal case is L31, which needs 12 vertices, and then everything else is bigger. So yes, for low dimensional cases, these estimates are not in the right direction, I would say.
So let me go one dimension higher. And, you mentioned PL structures. Can you say anything about exotic PL structures in dimension 4?
Okay, again, no. That's a simple, we can talk a bit later, but no is short answer.
Okay, one last question.
Thanks for the great talk. I was wondering, does the set of triangulations of a given space carry some meaningful structure that you could use to find something more about this minimal number of simplices? So is there a space of triangulations or something like that?
Okay, yes, there is quite some structure. So you can consider the set of all triangulations, and then I think it is connected in some weird way by stellar operations, but I think that the precise, some answers are known in low dimensions, and then it gets increasingly complicated. So I think Frank would be able to say something, but not much, because you somehow need to add points and then decrease points, add points, decrease points to do those operations. But it is connected by stellar moves, or what's it called. And I don't know anything about the global structure of this thing.
Okay, thanks.
Okay, in the rest of our lunch, I suggest to continue our discussion over lunch. Let's say the speaker again. So the lunch should be served right now, and we have exactly 1 hour and 20 minutes until the next talk. So thank you again, Petar, and enjoy your lunch.
Ja myślę, że ci, którzy dzisiaj byli. Oh, yes, thank you.